Hi everyone! Today I'm going to be giving you a high-level overview of my research in the area of computational sleep science. What I've done is I've taken a machine learning approach to the detection, diagnosis, and treatment of sleep problems. So if we take a moment to look at the big picture, there is this overall conjecture that our phenome, in other words our manifestation of self, is a function of our genome, our genetics, the fundamental DNA that makes up who we are, and our exposome, which is the entire exposure that we endure during our lifetime. Now, the genome has already been mapped by the Human Genome Project, but today we also have the tools to collect information of our exposures, and we can now attempt to quantify the human exposome. So what really is our exposome? It consists of our living arrangements, environment, air quality, job duties, disease exposure, digital exposure, all our collective experiences. The key thing to note here is that in order to alter our phenotype, meaning who we are today, we cannot alter our genetics, at least without extreme measures, but we can alter our expotype, simply by adjusting our everyday behavior. While an exposome is an incredibly complex entity to capture, we can obtain a partial picture as relates to some particular component. In this case, sleep. 1 in 6 consumers owns a wearable device. It's a $4 billion market, and it opens the door to an unprecedented amount of personal data. This can be particularly revolutionary for sleep science, where physical activity and sleep quality seem to have some correlation. By leveraging wearables as a catalyst for research, we can determine the effect of human activity on sleep and ultimately quality of life. So why is sleep even so important? There have been studies upon studies that have found good sleep to be correlated with health and happiness, and even more so that poor sleep can have serious side effects. It's a cycle. In fact, it's a downward spiral. Moreover, there are serious comorbidities that both cause and are caused by poor sleep habits. Poor sleep can often be a symptom of patients undergoing chemotherapy, suffering from epilepsy or arthritis, and poor sleep can cause exacerbation of diseases such as diabetes, obesity, and mental disorders. Here we have a diagram of the current sleep science process. Throughout the process, there is a need for manual annotation, so there is no mechanism for widespread screening. The gold standard of diagnostic tools is polysomnography, a technique developed in the mid-1900s. It's done in clinic and is a giant bottleneck, not to mention expensive. Home sleep tests are an abridged take-home version, and actigraphy is a new technique that leverages wearable devices but still requires manual interpretation. As for the therapy of minor sleep conditions, it involves impersonal lifestyle guidelines and ineffective or dangerous medications. Overall, we are left with an inefficient process, and it is clear that there is a need for a more data-driven sleep science approach, which is exactly what I've developed, a new, revised, data-driven approach to the sleep science process. One of the biggest advantages of this is we can distinguish between the screening and diagnostic stages. So let's start with screening. The first step was simply to automate the actigraphy, but rather than simply retrospectively evaluate the sleep quality, what if we could predict it beforehand? Simply by using an individual's activity during the day. In order to do this, I decided to explore the use of deep learning architectures, using simply the vertical axis of the accelerometer over time as x of t. The models were trained to minimize the cross-entropy between the predicted distributions and the target distributions. I tested a logistic regression model, a multi-layer perceptron, a convolutional neural network, a recurrent neural network, a modified version of a recurrent neural network called a long short-term memory cell, but ultimately designed a novel architecture called a time-batched LSTM, the best model of all, with an area under the ROC curve of 0.97 and an F1 score of 0.92. Given that strong ability to screen for sleep quality, let's dive into diagnostics. Deep learning methods are black boxes, so although they can predict with high fidelity, they lack insight, which is why I created a human activity recognition algorithm called RAHER, which labels the exertion level of the activity signal. The algorithm has 4 key stages, the first of which is an extraction of the annotation I previously showed. The second step is conducting a time series segmentation so that we have pairs of awake and sleep periods. The third step involves change point detection using hierarchical divisive estimation to identify points in a time series that divided into 2 components with the maximum divergence. This signifies a change in behavior. Lastly, using Troiano's cut point methodology, we can evaluate the exertion levels and aggregate these over the change point interval to give us our final labels. Now that we have a high-fidelity screening mechanism as well as a transparent diagnosis process, let's take a look at therapy. So far, we've taken a person's entire activity time series and predicted their sleep quality. But what if we could do this earlier in the day? In fact, if we predict a person will have poor sleep, we can intervene and give a recommendation that, if followed, could result in a good night's sleep. Using a training set of data built of raw hair output, we can cluster the midday activity signals. I use the Kolinsky-Arabesque index to determine K, and then use K-means for clustering. Within each cluster, we follow the same procedure to do a sub-clustering. However, the clustering this time is on the full activity signal. We can then compute the observed good to bad sleep ratio in each subcluster. Those above a certain threshold are activity targets for good sleep. Now, the second component of the methodology is to determine which recommendation to give. Here is where we can use that TB-LSTM deep learning architecture. If poor sleep quality is predicted, we compute the activity deficit between where the individual is right now and any of the target behaviors. The last step is to retrospectively evaluate whether these recommendations are effective. Two signals within the same cluster but in different subclusters show similar behavior until midday, but then exhibit different behaviors. We can thus identify who did or didn't follow the recommendation. And so here are some results. 81% of people predicted to have poor sleep but exhibited behavior following the recommendation ended up having good sleep. A huge impact. And that concludes my revised data-driven sleep science process. The result is an automated, proactive, robust, transparent, and dynamic process that can lead to a massive improvement in society's sleep quality. By building new computational methods and connecting the dots between physical activity and sleep, we can help improve the health, sleep, and quality of life of society as a whole. Thank you.